you on it. You learned it, even if you don't remember it later. I think that's true.
Yeah.
But there's got to be some window of retention, right? If it simply went in and came out, I don't think it would work.
I think you retain everything, but you can't necessarily recollect it at will.
I think the word you're looking for is recall.
Recollect.
Recollect too. I think this is the second day this term that I wore a tie for you guys. No, I wear the tie for you.
Yeah.
I do. I get dressed this morning. I look at my closet. I say, hey, I'm gonna wear that sweater. But if I wear that sweater, I can wear that white shirt that's all wrinkled and hasn't been ironed yet, and nobody will see the wrinkles. If I wear that white shirt, I should wear a tie. And I got dressed and I looked in the mirror and I said, I look like a lawyer. Maybe I should change. But when I decided it was okay to look like a lawyer for one day. So here we go. You guys should be done with your cards, right? Pass them to the center and the front. Pass cards to the center and the front. So when I originally drew the schedule, I forgot about academic advising day. Because, well, I never thought it was a useful day. And so I fully intended to have no lecture on Wednesday of this week and have lecture on Thursday of this week. And in fact, I fully intended that up until about 15 minutes ago when I realized that there's no classes on Thursday. So I switched it. The one we were going to do on Thursday is now going to be tomorrow, and I don't get to take Wednesday off. So we will have class today, tomorrow, and class on Thursday, and this is the week the labs are all screwed up too. We have lab Monday, Tuesday this week, but no lab on Wednesday and Thursday.
Yeah.
Wait, tomorrow Wednesday?
Yeah. No lab on Thursday.
There's definitely no lab on Thursday because there's no school on Thursday. Later, is your lab on Wednesday? I believe that there's no lab on Wednesday. Look at that, week 5. No lab on Wednesday. That's because section 1 has lab on Mondays and Wednesdays. Sections 2 and 3 and 4 have lab on the other days. And we like to keep them roughly lined up with each other and what they have completed. So yes, no lab on Wednesday. I imagine we'll still have session hours on the Wednesday that we normally have now. All right, up here. Today, I would like to switch topics and get off the sort of the idea of modeling. So we get off the topic of modeling and talk about design for manufacturability. So last week, this half of the room was full. Like, I feel like we're going to tip out the window now. If this was like a small airplane, they would make some of you move. Anybody ever flown an airplane where they make the fat guy move seats? Yeah. You know you're the fat guy when you're the one they ask to move. Absolutely. All right. So for the class up until now, we've primarily been talking about what the manufacturing engineer needs to know, right? So we've been positioning ourselves as the manufacturing engineer. And today, we're still going to remember what the manufacturing engineer wants to know, and still remember what the manufacturing engineer thinks about and needs to understand, but we're going to put on the hat of the designer for part of the day today. And we're going to talk about how do we design things so that they can be made. That's actually my whole goal with teaching the class and all the lab stuff that I do here at WPI, is to help engineers understand a little bit about how things are made so that they could possibly design things that can be made. And is it likely that a designer, either an experienced designer, a young designer just out of school, is it likely that this designer would design something that's impossible to make? I see a nod up in the back. So, I mean, I'm the eternal optimist, so I'd like to believe that if we can envision it, it's possible even if we don't understand how to do it. So I believe we'll have faster than light travel someday, even if I don't understand the map that gets us there. But what is certain that some designers do, whether they're experienced designers because they're lazy or young designers because they don't know any better, is we design things that are freaking expensive to make, right? And we don't know that we've done that. So what are let's try to stay in the order of my slides today. Because I like to talk, I'm going to actually look at my notes and stay in the right order. As the manufacturing person, so before we put our designer hat on, as a manufacturing person, what is it that we need to know in order to make our part? Your part. So Brian over here is the designer. What does Brian have to tell us in order for us to make the part that Brian wants? He's a star designer. Yes, dimensions. So we've got to know something about dimensions, right? We're going to know how long features are. What else do we have to know in order to make the part? Yes. We have to know the material it's made out of. What else? We do, but Ryan can't control it. So what are we asking Ryan for? What does Ryan have to tell us in order for us to make Ryan's part? We have to know that, but Ryan doesn't usually tell us. Ryan, yeah, we need to know our dimensions. We need to know our tolerances. We'll talk more about tolerances later today. What else do we have to know? Tolerances, material, dimensions. Yes. We might hear that, but I don't think we have to know it just to make a part. But the value that the customer places on it, right? We may, if so the value the customer places on it is $2, and we tell Ryan that it's going to take us $15 to make it, we might want to also tell Ryan you probably shouldn't make it, right? So that's good to have, so value. But and actually one of my engineering colleagues gets really, really mad when you're evaluating a design, a novel design, and someone asks about, have you thought about the cost of that? Or have you thought about how many units you'd be able to sell? Because his whole idea is we should be engineers and we should be innovating regardless of things like cost. But you're right. If we don't consider the value, companies go out of business. Yeah. When? I'm going to put that on the site too. But that is certainly important. I get, especially before we have this whole project registration system and something we use in the lab now, we get requests from students to have help make a project. They say, well, when do you need this done? ASAP. That has a couple of meanings. One, we don't do anything else until we work hard stuff. Another would be, we work on it when we get to it. And obviously that doesn't have the same meaning to Ryan if he needs it ASAP, right? So if you have a deadline, specify the deadline. Because at some point, we don't even want to accept delivery of it if it's after the deadline because maybe we can't ship it to our customer anymore, right? If it's the torch for the opening ceremony of the Olympics, after the opening ceremony, you don't need to keep working on making the torch, right? They've figured something else out. Okay, so we need to know tolerances, the dimensions. We need to know enough to make the part. How does the designer tell us these things? Brian, how are you going to tell me? You're going to give me a drawing, a sketch, a solid model, a list of specifications, a design matrix. There's several different tools that the designer has that you may use all in conjunction. Now, what I've got here for you is a sketch. We'll note that it is not drawn to scale, but it's got a sketch of a rectangular block that's half an inch thick, 4 inches wide by 5 inches wide, with a 1 by 1 inch pocket all the way through the center of it. It's made out of 60-60-126 aluminum, and all of the dimensions are specified plus or minus 1,000th of an inch. Is this enough information to make the part? So if this is the sketch Ryan gave us, and so sometimes the designer, all they really should need to provide is a sketch like this. You can draw it on a napkin. I use a piece of white paper and a Sharpie when I do this one, right? But that's enough information for the manufacturer to make that part, even if they never talk to Ryan. Correct? I think it is. I intended for it to be. If you're the manufacturer and you get to talk to Ryan, what's the first thing you're going to ask Ryan? Because sometimes the manufacturer does get to talk to the designer. Andre? Yeah, that's not the first thing I'm going to ask him. I might be curious, but that doesn't really matter. I've actually made parts where they will not tell me what it's for because of security clearances. I don't have a security clearance to know what it's for. I can see the drawing as long as there's nothing written on the drawing that says what it's for. Now, I'm not stupid, so I usually look at the shape and know what it's for. But that's besides the point. They haven't told me, so they haven't violated their security. So what's the first thing we're going to ask him?
Does the inside pocket have to have square corners?
Yeah, do we really super secret need those square corners on that inside pocket? Did I ever mention that in the socket? What do you do? What do you like? Okay. Less rating bugs. With WPI. Okay, so it would be a lot cheaper to make. We can do this, right? If we could put roundy rounds on the inside of those corners, what do we call those roundy rounds? Radiuses, fillets, I heard the technical term there. Yeah, I call them roundy rounds. Because I call most things that are circular in shape roundy rounds. Those things that rotate, I call them spinny spins. But it'd be really nice if we could put fillets on that, right? Because if we want to cut that pocket with an end mill, we are going to make a radius right here. And that radius is going to, at a minimum, be the radius of that end mill, right? Half the diameter of the end mill. So we're going to cut that. Now, Ryan, can we make round corners inside here? Now, Ryan says we can't do it. All right. What's the next thing you're going to ask him? I might go with our sure. How about a little bit round? Right, but no, Ryan is adamant they've got to be sharp 90-degree angles. So first off, if they absolutely have to be sharp 90-degree angles, how are you going to make it work? Right, you're going to mill it to be close to the right shape, and you're going to broach the rest of the way through. And broaching is just taking that square negative of the thing you want, of the hole you want, out of a hard material and pushing real hard to make it go through. So we could broach that, no problem. We could make that. It's a more expensive process for us to do, especially since we don't have any equipment at WPI that's set up to make it. I'm not saying we can't do protein at WPI, but we don't have any equipment for that. So what's the next option? We just gotta have square corners and we don't feel like broaching it because we don't have a 20-ton press to broach it with. And I don't know what the pressure would be, but it could be a 20-ton press. How else can you make that part without broaching it?
You could cut holes in the four corners.
So you ask him, why does it have to be sharp corners? And if he says it has to be sharp corners because I've got a mating part that's going to slide up in there, and that has sharp corners. Well, I think I'd start negotiating again and say, can we put fillets on the outside of those corners? But say we can't. Say he's buying that part. We can't do that. What we could do take our square shape that we need to make, drill a hole there, drill a hole there, drill a hole there, drill a hole there. Because he doesn't really need those sharp corners. What he really needs is the flat sides to mate, right? So we can remove some extra material in the corners so that there will be a radius there, but it won't impact his ability to put his part in. That's a cool idea. I like that one. What if he says, no, can't have it? My end customer won't accept that. Ryan's just the middleman. He's assembling this and selling it to the end customer. They'd be able to see this at the top and it would look ugly. Martha Stewart is the customer. She doesn't like ugly. What else could I do? Maybe you guys can't see that part. What if we have a part right here, held this part of it straight up to the mic, take a flat end mill with a sharp corner on it, and remove that material. Then we took another piece that was just like this, and we said, so say that's water. So what have we made? A 1/4-inch hole through from the end here, a 1/4-20 tapped hole here, and we use a fastener to hold it together. Maybe Ryan says, hey, that'll work. I don't care if there's bolts sticking out the side, I just can't have. Oh, look at this. We could. That would work. This should be a pretty line, right? We could even counterbore those holes so you can't see the bolt. Yes.
I was thinking like maybe you could weld those together.
Yeah, you can join them together. It doesn't have to be. Maybe you use some 2-part epoxy to stick them together. Maybe that's good enough for what Ryan needs, right? So if we get to negotiate with the customer, we might want, with the designer, we might want to think of, are there things we can do that would get the function? And so somebody said, we want to ask them why they need it. So you want to ask them, what's the function of this feature? What does it need to do? They don't actually have to necessarily tell you it's to aim a giant laser, right? They don't have to tell you that part. They can tell you it's to hold a mounting bracket. They can say, well, who's making the mounting bracket? Oh, we were going to send you the part. We were going to send you that drawing next week. Said, well, can we modify the shape of the mounting bracket so they fit together better? So if you get the opportunity and you're the manufacturing guy, talk to the designer. If if you're the designer, who wants to be a designer when they grow up? I know a lot of people come to WPI because they want to be a designer when they grow up. What do you want to design? Weapons, sorry. Weapons. Sweet. Like mirrors and regulators. What do you want to design?
We got this idea for an alternative energy.
Cool. So you're going to save the world, and you're going to reduce the population. All right. We can go right along with saving the world. You might just have to continue. I'm not going to take a stand here. Who else? Who else wants to design stuff? What do you want to design?
Military robots.
Military robots will carry the weapons. What else?
Automotive parts.
Automotive parts. I was waiting for that one. I expected that to be first. What else?
You might want to build armor.
Armor. For your windmills in case you start shooting them.
Well, I've also got an idea for
Right.
robots that would basically make it clear all of them.
Cool.
So they could like walk into
Don't piss this guy off.
They could like walk into a burning building and the building can collapse.
All right. So, but a lot of us, we envision ourselves designing stuff as we grow up, right? And so, if you know a little bit about how stuff is going to be made, one thing is so you can do automotive stuff. So you plan to work for a fairly large company, probably, or a custom shop. Okay. So one of the things that happens, especially when we're young engineers coming into the field, and especially if we get one of those great jobs where they take you, they put you for 6 months at this place, and then they move you to this place for 6 months, and then they move you to this place for 6 months, and then you're a manager at GE, right? It takes longer than that, but that's sort of the idea. When we get one of those really cool jobs, one of the things we end up doing is we end up interfacing with the guys on the shop floor. Because as a young engineer, especially if you're one of these management training programs, they need you to understand how to interact with the guys on the shop floor. Most schools don't teach that. So if you know some of the words, if you say words like tolerances, and if you say a tenth instead of a 10,000th of an inch, the cranky old machinist is out there on the shop floor, his or her favorite thing to do, and they love to do this, they'll do it all day long, and they will tell you they love to do it if you ask them about it, is to make that young engineer exactly what they ask for, especially when they know it won't work. So, but if you talk to them and you know some of the words, they're actually going to look out for you, and they'll help you keep from making mistakes that make you design things that don't work. So, anyway, I hope you take that on. As a designer, what do you want to avoid? So use your designer hat on now. You're a designer. What do you want to avoid?
Something so be a positive.
Yeah. Okay. I was thinking smaller scale, but we don't want apocalyptic things happening. Oh, I forgot. I had this one on a timer. Oh no, avoid being a kid with a cat, right? Right. So what we'd like to do is we'd like to make as few mistakes as possible. Whether it's to keep us from, I couldn't resist this screenshot. TCAD, you can buy that from Amazon. We might get something. All right. So how are we going to do that? What are the kind of things that kids with cats do? I've told you the term kids with cat, right? So what are some of the things that kids with cat do? Yeah.
Design expensive, hard to make parts.
Yeah, draw features that are easy to draw and look cool, but are expensive to make. What kind of features? Chamfers could be it. Right, so one of the things we want to think about is we're designing. I was on a roll when I was getting space station. Yeah.
It should invent a habit of finding late.
That might cause an apocalypse. But things that we're more likely to have happen to us in a machine shop. What kind of things do you want to avoid? So where do we want a chamfer as opposed to a fillet? Right, you guys, what do you got? It's really cheap to make chamfers on outside edges. Right, so if I'm cutting on the outside of my part here, it's really easy to knock that corner off with a chamfer, although we can do that with a fillet. If it's on the top edge, though, it's not really clear that that's the side view. If I've got a top edge here, and I put a fillet down here, and so we're looking based on the part here, then if I want to make that radius, I have two choices. I need to have a tool that has that radius ground into it, and then move that around the part, which I can do. They make those, you can buy those. Or I need to take like a ball end mill and take a whole bunch of passes to make that radius. Right? So those are my two choices there. If I drew my part with a chamfer, then we have lots of tools that have that 45-degree chamfer. And 45-degree chamfer is pretty common. So we have, when you see me drawing something, and I think you can see it, and I start walking away, you can tell me you can't see it. So we have a lot of tools, and so we can have a bunch of different depths, so we get a different size chamfers there. So chamfers versus fillets, we want to watch out for that. What other kind of things might we want to watch out for? Designing for manufacturing the machine ability now, right? Yeah, but that's not so much in the design. That's kind of on us as the operator.
Parts that are too fragile to machine.
So, yeah, parts that are too fragile to machine are things like thin walls. So we'll care about how, so if you have a thin wall on your part, it'll bend, right? It'll bend under the load of the cutting tool. We care about deep features. Why do we care about deep features?
The cutting part of your drill might not be able to drill that deep.
Yeah, we might not have tools to make those deep features. We care about having a lot of setups. We care about the materials that it's made out of. We talk about chambers versus fillets, right? Outside edges. We typically use those chambers to remove burrs. Now, a very common thing that you'll see on a drawing is a note that says, knock off all sharp edges. See it on drawings you go to the shop for all the time. What they're meaning there, so when you do your machining, let's say you've got a part like this, and you got your end mill here, and you're going to face off the top of the part. The tool path that does that. As the tool gets to the edge of the workpiece here, eventually that cutting force that's being applied to make the chip is insufficient to make a chip because you're disengaging from the material and the strength behind it. And what happens is the edge of the material bends over. And it forms a sharp edge right there called a burr. And so you see that note on the. That stayed on the screen. You see that over there. You see the whole thing. You see the outer thing. You just didn't tell me you could see the end mill. Right, we got our end mill, goes over there and makes a burr. As you see that note on the drawing, it'll say knock off all sharp edges. And so how could you do that? So they didn't tell you to put a chamfer on the part. You could put a fillet on it. You could put a chamfer on it, yeah.
If you face it and then contour it.
That's a good idea. We can do our next pass with our end mill here. Right? And we'll feed into the board like that and contour it. And it does absolutely get rid of that part. Just one there. There. So, good idea. And so you can actually keep doing that back and forth with lighter and lighter cutting forces. And eventually they get to what they're called microburrs. And it's a microburr, right? So you could do that. And I've seen that where if the bird's not too big, who cares about it? So one of the things you could do is you could go kiss that edge with a chamfer mount. So not so much to put a chamfer on the part, but to have it go along there and just sort of up to the edge. It'll make a little small chamfer. But you'd rather have a micro chamfer than a micro burr. Because anybody ever get cut with a piece of sharp metal? Where is it usually sharp?
Corner.
On the corners, on the edges, where there's burrs. It's usually the burr that cuts it. So that's why you'll see that kind of a note on there. So they may not design in a chamfer, but you can still take your chamfer mill and put a little chamfer on it, and they will accept the part. A lot of designers don't even think about that, and so you get the drawing, and it's covered with sharp edges. And so what else is bad about sharp edges on our parts?
Force concentration?
Yeah, stress concentrations, right? And so our stress is force applied to an area, right? What happens if the area goes to zero? Stress goes to infinity. That's exciting. It's when things break. And so we more worry about that in the inside corners of the pocket. So this is our exhibit here. So people tend to be more worried about that inside corner of our pocket, and if you have a sharp corner there. So Ryan, by the way, dude, you don't want sharp corners. Has anybody ever done SolidWorks finite element analysis stuff? That part's going to fail, and it's going to fail right at those corners because of that, right? So you want to have our little holes or something, right? So we want to put our fillets on inside corners. We'll reduce stress concentrations and do that. All right, so chamfer fillets. Tolerances. Somebody said tolerances, right? I couldn't resist. Weird sound though. Oh, it doesn't do it. This one. I'm H2O intolerant. It's like one of the best lines from any movie ever. Usually I quote movies. I don't usually play them in class. All right, so tight tolerances, loose tolerances. So what's the tolerance again?
How far off stated measurement?
Yeah. How strictly Ryan cares if we actually made the part he asked for, right? Because Ryan doesn't really want the part he asked for. He wants a part that's good enough to sell to his customer, right? So it's how closely do we have to hit those dimensions that we specified earlier. And so the tolerances for us as the manufacturing engineer impact which machine tool we're going to use. So as a rule, more expensive machine tools can hold tighter tolerances. When we say the tolerance is tighter, that means the variation that Ryan's willing to allow us is smaller. So plus or minus a 10,000th of an inch. The tooling that we use. So if we use, here's our choice of tooling. There's our collet. There's our end mill. And here's our collet. There's our end mill. If either one of those tool setups can make the part, which one do we use? The short one, right? And why is that? Because our deflection, the little d, is proportional to the length cubed. It doesn't even look like a d. This is there's our little d symbol, right? And I looked it up. That's the symbol for proportional. Little fish. So our deflection of our tool is, so what's going to happen when our tool deflects?
Bad tolerances.
They might be great tolerances,
Well, it won't be exact. It won't cut
but
the
they
hole.
won't be, they'll be loose. The machine tool doesn't make tolerances. The designer makes tolerances. The machine tool has capability. That's one of the things that we'll say. But people say, oh, my machine can't hold that tolerance. Well, really, my machine doesn't have that capability. And so what's going to happen if the tool deflects, the part's going to grow. If we're making a boss on the part, like this, it's going to be wider at the top than it is at the bottom, right? So it'll be like that. Is that right? Why not? When the cutting force is here, the tool's going to deflect like that, right? So the tool deflects like that, it's going to be wider at the bottom, not at the top. I'm not going to try to draw it again now. I'll fix it in the video later. I'll turn the board upside down. All right, so how do you get, so, all right, we said expensive machine tools, fancy tooling. An operator that can go set up the part and make the base for your Sterling engine, say. That was our production part. You guys have all seen this. It's a couple setups, flips it over. There's, do you guys measure anything to take it out? What do you measure?
Overall size.
The overall dimension, yeah. And so we go that overall dimension that we measure when we take it out. The operator that can run that machine and successfully make parts all day long, day after day after day after day, costs about $15 an hour. If you change that dimension, the tolerance, to plus or minus a 10,000th of an inch, as opposed to probably plus or minus a quarter of an inch is what it should be. I don't know what they tell you it is in the lab manual, but if you change that to plus or minus a 10,000th of an inch, then the operator that can set that up and keep checking it to make sure that it's running correctly, about $50 an hour. That's a big difference in cost. And that guy is hard to find because they're all 50 years old and they all already have a job. Nobody's making that operator anymore. So that's expensive. It's more expensive inspection costs. One of my favorite things to do, when you come to me with a tolerance that's unreasonable, that happens all the time here, right? Because you don't know what's reasonable until I tell you. So when you come to me with a tolerance that's unreasonable, I say, how are you going to measure that? And when you say, I don't know, I say, no problem, I can make it. Because if you can't measure it, it doesn't matter, right? All right. So, go.
What is a reasonable tolerance? Depends on
Good.
That's what they're